So methane is a molecule that has this chemical formula: 1 carbon and 4 hydrogens. A very simplified Lewis structure would take and put 4 hydrogen atoms all the way around, looking like that. Now, the goal of this video is I want you to be able to use atomic orbitals to describe the bonding in any molecule, but in this case, methane. And in order to do that, you need to understand hybridization states. But before we jump into that, I want you guys to gain an appreciation of the molecular geometry of methane. Okay. And so I'm going to draw methane in this program here. And so we have a carbon, and the way I drew the Lewis structure is I went like this. I drew that molecule there. Now when you take a look at the way I've drawn that molecule, you will see that the bond angles between this bond and this bond right there, the way I've drawn it is 90 degrees. But based off of Vespers theory, that's not true, because we want the electron clouds to get as far away from one another as possible. So carbon actually does a tetrahedral geometry that looks like this. And now this bond angle between those two bonds right there is going to be 109.5. So this program here allows us to take a look at that. So even though I drew methane on the left here as a Lewis structure and all 4 hydrogens are in the same plane of the atom, that's not true, because take a look at the ball and stick figure on the right. What we're representing is a tetrahedral geometry. So I want to highlight some hydrogens here, that one and this one, okay, shown in the molecule there. Now look at that. Those 2 hydrogens are in the same plane. If we go and draw a line from the very top all the way to the very bottom, you see that there's a plane of symmetry. So those 2 yellow hydrogen plane. But then the other 2 hydrogens, this one and this one, they are not in plane with the 2 yellow hydrogens. They're out of the plane. And so this hydrogen right here, you can see that it's sticking towards you. It's sticking out of the plane towards you, whereas this hydrogen is sticking out of the plane away from you. And so a better way of drawing the tetrahedral shape of methane is to use wedges and dashes. And so we would take this hydrogen right here and actually draw it as a wedge. And so you can see now this hydrogen there, it's a wedge. And that wedge means that that hydrogen atom is sticking out of the plane towards you. Whereas this hydrogen right here, we would give it a dashed line or a dashed bond. And there you can see that is sticking away from you. It's sticking away from you out of the plane. And remember what the plane is? It's those 2 highlighted hydrogens, and that plane just is from you just draw a line from the very top of this atom right here, this one that I'm pulsing through, and this one. Draw a line from the top to the bottom all the way through, and there's going to be a plane of symmetry. But still, the way I've drawn this, the bond angles kind of look like that they are 90 degrees from one another. So with the wedges and dashes, you just clean it up a bit. And this is how you would clean it up. You would draw 2 of those bonds in the same plane, like this. But instead of going 90 degrees, you would just give it a little 109.5 degrees. And then you would draw your dash bond like this, and your wedge bond like this. And then we would just change those back to hydrogens, so we have methane. And that's how you would draw that molecule. And so you can see that these two hydrogens right here are in the plane, and you can see that when I rotate the molecule like that. Another thing that you need to be aware of is that we could take this molecule and rotate it in a different way. We can represent it in a different way. Okay? So what if I took the molecule and rotated like this? How would we represent that? Yeah, like that. How would we draw that one? Well, let me do it right here. We would have our carbon, and I see that there's two bonds sticking out at me. This bond and this bond. Okay, so let's highlight those. There's that hydrogen and that hydrogen. Do you see how it's sticking out at you? And then the dashed bonds like this. And so this hydrogen is that, not that. Oh, now it kind of messed up. But those dash hydrogens right there are the two hydrogens that are pointing away from you. Okay? So we can represent this molecule. We can rotate and spin these molecules. You can see we can just spin them. And we can draw that representation on a piece of paper. Okay? So that's what, and so getting your hands on a model kit is really good to help you guys visualize this. So let's work with this one right here. Okay. So now that we've gained an appreciation here of the molecular geometry, let's figure out the orbitals that are going to be involved in the bonds. Okay. So what we're going to do is redraw methane like this. Okay. And we are going to take a look at all those bonds there. So we have 4 bonds right there. And we want to represent how are those bonds formed. What atomic orbitals are used to form those bonds? That's what we're trying to figure out. So when we look at our structure here, we see that we have 1 carbon. And carbon in the ground state has an electron configuration that looks like this. And what I'm drawing in those orbitals there are the valence electrons of carbon. And then I see that we have 4 hydrogens, and in hydrogens are going to, the valence electron in hydrogen is going to be in a 1s orbital. And we have 4 of those, so I'm going to times it by 4. Okay. Now we have to figure out the hybridization state of the carbon atom. And because this carbon atom has 4 electron groups around it, by bonds, we are going to, that is going to be sp3 hybridized. So that means we have to take this ground state configuration and hybridize an s orbital and 3 p's. And we're going to hybridize them to make them all degenerate, or all the same energy level. So that's our sp3 hybridized orbitals now. And it still has 4 electrons. And so we have this. We have those electrons that we have to account for in the bonding, and then 4 of those. Now that we have a sp3 hybridized orbital, what does that look like? An sp3 hybridized orbital is simply taking a s orbital plus a p orbital and combining them. And so we're going to have something that looks a little like something like that. And then there's going to be phase, a positive and a negative phase of that sp3 hybridized orbital. And so now it's those orbitals that are on the carbon. So I'm going to now look at this carbon right here, and we are going to have a sp3 hybridized orbital right here. But to make the drawing a little bit more clear, I'm not going to draw the little lobe, this little lobe right here. I'm going to omit it. But we have to remember that it is there, and I'm just on purpose not drawing it in. So I'll draw an sp3 hybridized orbital there for this bond. And now we have this bond right here, so we will draw the sp3 hybridized orbital coming off this way. And then this wedge right here, that you aren't going to be able to draw it very well in like a wedge. You just draw the orbital. Okay. And then we have the dashed one right here, like that. And within those orbitals, those sp3 hybridized orbitals, we see that there's 4 electrons. And so I'm just going to draw those in like that. Now, what is a covalent bond? It's the sharing of electrons. So when we look at this carbon-hydrogen bond here, we know that there is a electron coming from the hydrogen and an electron coming from the carbon. And when those 2 electrons are shared between the hydrogen and the carbon, we form that covalent bond. And so we have electrons. Let's give it a different color here. Let's give a yellow one here. So one of the hydrogens is going to come with a 1s orbital, because that's what orbital the electron is in for the hydrogen atom. And a s orbital is spherical, and a p orbital is that dumbbell shape. And how many electrons does hydrogen bring to the game? 1. And so what we have here is this orbital overlap. Let's see if we can change the color here. So what we have is right here is orbital overlap between the 1s orbital and the sp3 hybridized orbital of the carbon. And when you have orbitals interacting head to head, that means that that is a sigma bond. We represent that with the sigma, the Greek symbol sigma. So let me explain what head-to-head means. Okay? Is when you have, let's draw ourselves a sp3 hybridized orbital and a s orbital. Okay? If we take that s orbital and get it on the side of the sp3 hybridized orbital like that, that is going to be considered pi bonding. Pi bonds. But if we take that s orbital right here and put it head to head, that is going to be a sigma. A sigma bond. And I'm going to give another example of pi bonds in the ethylene video. But in this video, I'm just going to focus solely on the sigma. Head-to-head overlap. Right there. And so what we have for methane is we have 3 more of these that we have to account for. So I've already accounted for this hydrogen and this bond And so that bond right here that's shown in green is what's shown in the pink overlap right there. So now we just have to bring in the other 3 hydrogens. So this is representing a hydrogen, and there's going to be orbital overlap, another 1s, and another 1s. So what we have here is sp3 hybridized orbitals overlapping with 1s orbitals. So what we want to be able to do now is to identify the orbitals that are used to form that bond. So if I asked you what orbitals are used to form that sigma bond, you would say, well, the carbon atom is sp3 hybridized, and it is forming a bond with a hydrogen atom, and the hydrogen atom is coming with a 1s orbital. So if I asked you what is the orbitals used to form that bond, it would be the same exact answer, like that. Okay, and those would be sigma bonds, because when you go back to this picture right here, it's head-to-head overlap. Okay. And if you guys go to your textbook, you will definitely find prettier pictures of these orbitals, but you need to be able to draw them. And so practice that, look at the textbook, and hopefully this video explained it in a way that you can understand it. And as always, if you have any questions, please reach out. I'll be more than happy to help.